Yeah, thank you. And thank you very much to the organizers for inviting me to speak and for organizing this very nice conference. Okay, so we're going to start with some very kind of broad motivation that I think most people here are probably on board with, and eventually we'll get to some questions that are in Lie algebras, which I think most people here maybe aren't on board with, but then like I'll bring you there. Like, so by the end, you'll also want to know the answers to these questions in Lie theory, hopefully. Okay, so let's start with some broad motivation. Okay, so the broad goal is to understand rational points on curves and also Selmer groups for Jacobians of curves in families. And the broad method sort of pioneered by Bargava and his collaborators is to count orbits in some related representation. Okay, let's talk about some examples to make this a bit more clear. So one example that I think, the board needs to be a bit lower for me, sorry. Just there. So sort of the primordial example that I think a lot of people are already familiar with was work of Bargava and Shankar on two Selmer groups of elliptic curves. Right, so we'll let F be our family of elliptic curves over the rationals. And the theorem they proved was that if we order these curves by height, then the averaged size of the two Selmer group is equal to 3. And their method of proof was to count orbits in the following representation. So we'll let P4 be the spaces of homogeneous degree 4 polynomials in two variables. So this has a natural action of PGL2, which you should think about as acting on the two variables. And there's a relation proved by Birchin, Swinnerton, Dyer, sort of a classical relation between elements of the two Selmer group of an elliptic curve and certain integral orbits for this representation. So Bargava and Shankar developed tools to count these orbits, and that's how they proved the results. So for other examples, I've written the following handy chart. It's hard to write them all down, right? Okay, I think people can see this. Yeah, I can explain some of the notation. So the first line of this chart is what we just talked about. For the second line, maybe I'll say something about my terminology. Okay, so when I say odd hyperelliptic, I just mean that it's given by an equation y squared equals 2g plus 1 plus, say, a 2g minus 1. A 2g minus 1. Right, so the odd just refers to the fact that this exponent is odd. So that's odd. And so for that, oh, I didn't put the extra parenthesis, okay. So for that, they were looking at SO2G plus 1 acting on a certain space. I'll just tell you what this notation means. So if I have an n by n matrix, I want star to be the involution that just flips the matrix over the anti-diagonal. So the space they were looking at was, so little SL 2G plus 1 is just traceless 2G plus 1 by 2G plus 1 matrices. And they were looking at all of the matrices that were fixed under this involution. So everything, I guess you could call it like anti-symmetric. So a symmetric matrix would be fixed under the normal diagonal. This is just fixed under the other one. That was Bergava and Gross, and I just have another line. So for the 5 Selma group, they were looking at a certain representation of SL5 cross SL5. So that's the 5 stands for the defining 5-dimensional representation of SL5. So just normal 5-dimensional vector space. Okay, and you can keep going with this. I mean, so like, I didn't want to fill like many boards with this chart, but like you can kind of list all of the representations that show up attached to these different proofs. And some natural questions that come up if you're staring at charts like this. So first of all, you can look at this column with the representations and ask, like, what characterizes these representations? Like, which representations are showing up when you're looking at these Selmer groups? So which representations appear? And the second natural question you can ask is, okay, so when Bergava and Schenker were looking at the two Selmer group of elliptic curves, they had this classical correspondence between elements of the two Selmer group and these homogeneous degree 4 polynomials. So they're using this kind of classical relation. And in general, like how do you attach a representation to a family of curves is a natural question. Like, is there a way to do it that's not sort of case by case, like looking in the literature, like, okay, like what can we attach? So is there some general way to associate a family of curves to a representation? So is there a general, maybe construction that associates a family of curves to some representation? Okay, so some answers. So around the time I think that Gross was working with Bergava, he was also working with my advisor on something totally unrelated, related to the local Langlands correspondence. And in that work, graded Lie algebras were showing up. And Gross, looking at this column of representations, realized, like, hey, the representations that show up when we look at graded Lie algebras actually are the ones that show up in this column. So the answer to the first question is that all of these representations appear when you look at graded Lie algebras. Yeah, so what we'll do next, right? So what we'll do in like 5 minutes is I'll tell you how to construct a graded Lie algebra and show you how the representations appear. Yeah, for sure. So you don't need to know about graded Lie algebras before the start of this talk. So the representations come from, we'll make that more clear, graded Lie algebras. Okay, and for 2, so around this time that Gross realized this, he had a student, Jack Thorne, and he said, oh, can you like look into this further? And so what the sort of philosophy for 2, I feel like I didn't use, let me see what word I used, because I think I liked it. The approach. The approach that he sort of started. So started by Thorne. Is the following. So if you start with a graded Lie algebra, so this is sort of big picture, and then we're going to go into details. But there's a very natural way that just comes from the definition to construct a representation. So a group G and a representation V of G. So this arrow comes from the definition, and we'll talk about this next. And what Thorne started was to construct this other arrow, which starts from a graded Lie algebra and constructs a family of curves. So this arrow will be the main focus of the talk. So we can do this in certain cases, but we don't know how to do it in general, but that's sort of like what I'm currently working on. So I'll tell you what we've got so far. But you might think, like, what's the benefit of this approach? Like, why are we throwing this other object into the mix instead of just looking down here? And there's sort of 2 reasons. So one reason is that it's nice to have like a more general construction that's not sort of like ad hoc family by family. And so if we have a uniform way to associate these 2 things, that's nice. And the second reason is because the orbit counting methods developed by Bargava and his collaborators, they do use a lot of sort of case-by-case analysis, especially like if you know about these things like in this part where you're cutting off the cusp. And if you have sort of a bigger picture to work with, you have more tools to use when you're doing this process. So you can use tools in Lie theory to count orbits, basically. Okay, so I promised you that I would talk about this arrow. So first, the next things we'll do is define a graded Lie algebra, or show you how to get one, and show you how to get this arrow from a graded Lie algebra to a representation. And then we'll talk about the other arrow. But any questions before we do that?
Maybe one family of curves and not a billion varieties.
Oh, it's a good question. It's sort of what comes out of the construction. So you'll see like, so what will come is we have a natural way to go from certain Lie algebras to families of surfaces, and that was sort of developed in the 1970s. And when you add the graded in, it allows you to go to curves. So it's sort of like the natural thing that comes when you kind of try to generalize this construction of surfaces, basically. Yeah. Okay. Let's talk about, yeah.
When you look at this, do you think that the problem is to write down equations for the 2 descents and the 5 descents in a very explicit way? It doesn't appear in the diagram.
Right. So, right. I mean, there's sort of like, this is sort of like big picture and you don't get all the details, but you do, you do get to skip over some of the...
There's no arrow starting from family of curves in your diagram.
Right.
No, there won't be?
No, I mean, for today, we're just looking at this diagram. Yeah, no, these are good questions. Okay.
What goes with the peer in your family? I mean, like things like plane cubics that don't necessarily have a rational point.
So, like, what appears in the and what appears when you do this construction?
Some of the curves you'll appear will be things like, say, without a point, like twisted elliptic. There are choices for an elliptic curve that don't have a rational point.
Right. So this doesn't give you. This won't give you like every single thing you might be interested in.
You can
Yeah, they're sort of more, I'm like giving you kind of like the very big picture. There's sort of more work to do. Yeah, okay. Okay, let's talk about graded Lie algebras. Where do I guess that can go there. This can go here. And I'll give you a general construction, so how to construct a graded Lie algebra. So we start with H, a reductive, so say a connected reductive group. We're not going to worry about what fields we're working over because this just works for everything. And start with an automorphism of H of finite order. So say order M. Okay, so if you have an automorphism of H, your reductive group, you get an automorphism of your Lie algebra. So I'm using curly H for the Lie algebra of big H. Okay, so what you do is, so let's let zeta be an mth root of unity. And then let's define Hj to be the zeta to the jth eigenspace for theta. So then, okay, sorry, I know this is disappearing. I'll switch it in a second. So then you can decompose H, your Lie algebra, into a direct sum over J and Z mod Mz of Hj. And this is an M-graded Lie algebra. We'll see, I'll do an example in a second. Is that, okay, there. Yeah, so I said it doesn't matter what fields we work over, and indeed, everything we'll be working with today you can get in this way. And okay, so like what if the field you're working over, say we're working in characteristic 0, because that's easier. Say the field you're working over doesn't have an mth root of unity. It doesn't matter for all of the gradings that we're interested in because everything will be defined over Z. So, you know, take some data in your algebraic closure and then do this and then intersect with your whatever field you're working, the points over whatever field you're working over, and you'll get something. Okay, I think I want to go up like that. Okay, so this is how we're getting our graded Lie algebras. How do you get the representation? So like, oh, it's going by itself. It's going by itself. Okay, so how do we get this arrow? So the way to define G is take H, look at the fixed points for theta on H. This might not be connected, so just take the connected component. And then this naturally acts on each of the eigenspaces. And so we tend to work with the first one, so we'll let V equal H1. So this gives you this arrow here. Let's do an example so that this becomes more clear. So let's start with SLN. And let's let theta be defined by theta of an n by n matrix is equal to, so take the inverse of A and then reflect it over that anti-diagonal. So then if you look at the fixed points, you get SON. You get split SON. And if you look at, okay, so the algebra of SLN is just traceless n by n matrices. And d theta in this case is equal to, so d theta of a matrix A is equal to minus A star. So what does it mean to have -1 as your eigenvalue here? It means you're fixed under this reflection. So your V, your H1, is just equal to exactly the space you see in the second row. So this is all the A's such that A star equals A. So we get back the representation used by Bargava and Gross. And in fact, if n equals 3, if you're looking at 3 by 3 matrices, then G is SO3, which is isomorphic to PGL2. And then this V as a representation of PGL2 is isomorphic to P4. So we get the representation from the first row of the chart. Okay, so that's how you go from a graded Lie algebra to a representation. Questions about that? Okay, so let's talk about this other arrow. So I'm going to try to make this not super technical. And the way I'll do that is by mostly doing examples instead of defining everything. But hopefully you'll end up with some sense of how this works. So this is part 3. Oh no, I forget I remember what I was going to say now. Okay, let's go back to our chart. Sorry, so now you know how to do this like graded Lie algebra stuff. Let's go back and fill in a column of the chart, right? So there's secretly sort of another column here, which is what Lie algebra does it come from? So the first one, as we saw, comes from SL3. The second one, as we saw, comes from SLN. Both of these with a 2 grading, right? So you're taking an involution. The next row actually comes from a 5 grading of E8. One of the best Lie algebras. And actually, so I'll fill in another column here. So Jack Thorne and I, using these combined methods, using like graded Lie algebras, we're able to prove that the 3-Selmer group for the Jacobian of genus 2 odd hyperelliptic curves has average size 4. So this is genus 2 odd hyperelliptic. And so the so the way the column should work for us is we started with E8. We looked at a 3 grading on E8. The G that comes out of it is SL9. The representation that comes out of it is wedge 3 of the standard 9-dimensional representation of SL9. So that was myself and Thorne. And I should say that we really use Lie theory throughout our proof. I think other people tried to do it, and there wasn't sort of enough there to actually finish the proof, but we were able to do it using the theory of graded Lie algebras. Okay, yeah. So let's talk about the thing I've starred on the chart over there. So this is we'll start a bit by talking about Sadowi slices. Okay, and I'll do this, like I said, through examples. So let's look at the following examples. So let's look at SLN. So if you take a matrix in SLN, so this is traceless n by n matrices, and let's look at the characteristic polynomial of A. So the characteristic polynomial of A, okay, so it looks like, so it's a degree n polynomial with no trace. So a(n minus 2 x to the n minus 2 plus down to a0. So we can define a map pi from SLN to affine n minus 1 dimensional space by taking a matrix A and sending it just to the coefficients of its characteristic polynomial. So a n minus 2 to a0. Okay. So in the 1970s, this guy Slattery defined a transverse slice, he called it, of this map. Okay, and the idea is that, so we've got, so what is it? It's an affine subvariety. So it's inside of SLN. We've got our map pi here. And if you restrict pi to S, the fibers form a family of curves. And it's what's called a semi-universal deformation of a simple singularity of type an minus 1. So if you don't know these words, that's okay, but basically the fiber gives you a deformation of a certain singularity. And this is what he was studying. So such that the fibers of pi restricted to S give a family of surfaces. And I can show you, let's do an example so that you actually believe me. I'll just switch. This is 3. So, sorry?
Which type of singularity?
So if you're looking at SLN, it's type an minus 1. He did this, I'll say this in a second. He did this for any simple Lie algebra that's simply laced, and you always get a deformation of the singularity that gets given by the Dinkin diagram of that Lie algebra. Okay, so this has to go up, and something else has to go down. Okay, let's stop it there. And then let's say T2 goes down. There, now you can see that. Okay, and where do I guess I want to go here? Yeah, let's do an example, because you can actually, if you work at examples, you can actually see what this looks like, which is nice. So an example, if we're looking at just n equals 3, then S, depending, okay, so there are some choices. If you make the choice that I want to make, your S looks like the following. So we've got A, 0, 1, minus 2A, 0. This we'll say is B. This we'll say is C, D, 0. So it's all matrices of that form. And you can work this out if you get bored, but so say this is A. So if pi of A is alpha beta, then A satisfies the following equations. So it satisfies 2A cubed plus 2A times alpha. Sorry, this should be an A. Yeah, thank you. Plus 2A times alpha plus, I think it's B times D. equals beta. I'll double check it to make sure I didn't script the coefficients. Yeah, B and D, yep. And so you can see that this corresponds to a surface that looks like x cubed plus alpha x plus yz equals beta. Okay, and so then what Thorne did was he looked at these slattery slices in the grid. Just ignore that as it disappears. He looked at this in the graded setting. Specifically, we can go back to, okay, so our H is SLN in the example we're continuing with. And so remember we had H decomposed as H0 plus H1 as before. So meaning using that theta that we defined right there. So in our example. So what Thorne showed is if you look at pi restricted to S and then you intersect X with H1, you get a family of curves. And I should put a star here because you have to make certain choices. For S. So basically, when you're defining S, there are some choices to make, and you have to define it to act nicely with your grading. So you can see in this example here, so we have that matrix A. When will it be in the -1 eigenspace for our involution? It'll happen when B equals D. So that would mean, in this case, your Y equals Z, and you get an elliptic curve. Right, so using what Thorne's construction, you can go from your SL3 to grading to get elliptic curves. I wrote this on the wrong side. Okay, so I should have put it on this side because we already showed that you also get PGL2 acting on P4. Right, so we get the same objects as in our original example, except we have kind of a bigger picture here with this bigger Lie algebra. And if you do Thorne's construction, I can put this there. Starting with just SLN instead, right? So using this setup, you get these curves studied by Bargava and Gross, right? So we obtain the things that we kind of already knew were there. But like we get additional things that sort of hadn't been looked at before. So Jack and I also looked at the two gradings of E6, E7, and E8. And you get families of curves there, and you can analyze them using this graded setup. Okay. Yeah, so this was like all one big example using SLN. So maybe I'll say something about like what generality this holds in. So
in this example, you're getting elliptic curves, not curves between this one. So there's no question of the two covers appearing in this setup.
right. So
I'm just asking. Initially, you started with a two-summer group, so it's more two covers which might have no rational point. And here you've seen something with automatically as a rational point.
yeah. Yeah. Right. Okay. So what generality does this hold in? This board really wants to go down. Okay, so Slattery, as I mentioned before, so he was working with all simply laced Lie algebras. So this is H, simple, and simply laced. So type A, Z, E. He did some stuff with non-simply laced, but just for, for the initial purposes. And Thorne was working with, okay, so like H again, simple and simply laced, and also only with 2 gradings. And not only just 2 gradings, what are called stable 2 gradings. Okay, I'm trying to avoid a lot of technicality. Yeah. I'll say what stable means, yeah. So stable means that the representation of G on V contains a stable vector in the sense of GIT. So a vector whose orbit is closed with a finite stabilizer. These are kind of the nice gradings to work with because the orbits look nice enough. You have nice enough orbits. And so every simple Lie algebra has a stable 2 grading, often called the Cartan involution, right? So studied like by many people. This is sort of an old thing. Okay, so that was the setting that he was working in. So a very natural question to ask is, what about the other gradings? So, for example, here, so basically the M in the grading, like the number of graded pieces in this chart, always corresponds to which Selmer group we're looking at. So like here, we've got a 5 grading, right? So that doesn't fall in this setup. Here, we have a 3 grading. It doesn't fall in this setup. We had to do extra work to kind of, the arrow is erased now, but to like make that arrow for that. So the big question is, can we generalize this to stable M gradings for arbitrary M, but also for non-simply laced Lie algebras, right? Like what happens if you look at a non-simply laced Lie algebra? Okay, and I don't have all the answers, but I'm going to tell you a little bit about sort of what you have to do to get there and what we have so far. Okay, let's bring number 1 down, I think. A little pause. At least we don't have to wait and wash the board in between. That always adds like so much time to a talk. Okay, so what I'm going to do, because I want to avoid giving you sort of all of the technical details, I'm going to tell you sort of the key things that Thorne needed to build these slices. And then tell you what the issues are for extending this. So, so sort of some keys to Thornes construction. So the first thing that so without giving you a lot of technical details, Slattery slices sort of depend on looking at centralizers of what are called subregular nilpotent elements in the Lie algebra. Nilpotent, just for SLN, nilpotent literally means nilpotent, that you take a power and get 0. Subregular has to do with the centralizer. For SLN, it means that the centralizer has dimension n+1. Okay, so that's what Slattery was using. What Jack had to use, what he proved, was that H1 contains the subregular nilpotent. Right? If we want this construction to work sort of on a graded level, we need a nilpotent in H1 to do the job. So the first thing he proved is for a stable 2 grading, H1 contains a subregular nilpotent. The second essential thing that he used was, in this case, so in our stable 2 gradings, if you take a subregular nilpotent in H1, this implies, all right, so you know the dimension of the centralizer in the whole Lie algebra, but then you have to think about how does this centralizer break up into the graded pieces, right, if you want to do this in the graded setting. So if E in H1 is subregular, this implies that the centralizer in H0 of E has dimension 1. What does that mean in our case, right? So basically, it means that if you start with Slattery's construction and kind of restrict to the graded piece, you're going from the correct dimension to give you surfaces to the correct dimension to give you curves, right? This is saying that if the centralizer in H0 has dimension 1, then the centralizer in H1 has dimension like 1 less than its dimension in the whole Lie algebra. So basically it's saying, like here, it's saying we're knocking off 1 dimension. So instead of getting surfaces, we get curves. That's sort of how you should think about it. So to generalize, what we need to do is to understand nilpotents in the first graded piece of an arbitrary graded Lie algebra, and also understand what their centralizers look like, because the centralizers would then give us these transverse slices. So I'll talk about sort of the questions we have and what we know and don't know. So this, I think, is part 4. So this will be about stable M gradings. And I don't really have any big results. We have like kind of a small example, but this is all joint with Jeff Laga. Okay, so the first question we asked, which is the natural question if you look at these 2 keys here. So what are we doing? So we've got, our setup is that we've got H, we've got a stable M grading on H. So stable meaning the same thing, that we have these nice orbits. The first question we asked is if we take an arbitrary, and H, just a simple Lie algebra. The first question is, does H1 contain a subregular nilpotent? So we were hoping the answer would be yes, because then we would just be able to kind of follow along with what Jack did. But the answer we found out is no, not always. There is the first example we came up with that contradicted this was a certain 6 grading on D4, so SO8. Okay, so that was like a bad start. The second question we asked, we were like, okay, so maybe this isn't true in general, but maybe we can just restrict to the cases where it is true and then keep going from there. So the second question we ask is, if we have a subregular, so does E in H1 subregular, does this imply, like in the stable 2 grading case, that the centralizer in H0 of E equals 1? Because that will give us the right dimension to have families of curves. The answer, again, is no. Right, so yeah, again, there's an example for G2 where this doesn't happen. Okay, but then we realized we are actually asking the wrong questions. So we're so focused on this subregular business because that's what Slattery did. That's how Jack generalized it. But it turns out subregular is not necessarily the right property to look for. The right property to look for is actually this one. So we just got rid of question 1. We got rid of all the words subregular. So the revised question is, does there exist a nilpotent E in H1 such that the dimension of the centralizer in H0 of E equals 1? Right, so forget about subregular, let's get the right dimension to have curves. And the answer is, in every example we've looked at, this is actually true. And so we have one example / proposition, which is what I'll end on. Oh no, I did the wrong thing. Laga and then on. Okay. I'll write it and I'll use words maybe people don't know, but I'll say something about them. So let's assume that so we're going to take what's called the Coxeter grading. I'll say something about it in a second. Let this be the Coxeter grading. So then there does exist an E in H1 such that the centralizer in H0 of E has dimension 1. And I'll just say so every simple Lie algebra has a Coxeter grading. So this is nice because it's completely uniform. We don't have to think about simply laced. It just works in general. The curves, unfortunately, that you get when you do when you continue the process are boring. But the reason they're boring is because, okay, so basically a stable 2 grading has H1 as big as possible. So you have lots of room for stuff to happen, lots of room for interesting things to happen. What the Coxeter grading is, it's the grading such that, the stable grading such that M is maximal. So each piece basically is as small as possible with still giving you the stable property. So H1 is so small that nothing interesting could happen is what happens. So the curves just look like x to the n y equals c as c ranges over whatever field you're working over. It works over any field, so so this is Coxeter grading over F. Or H is over, yeah. H is over some field F. So the curves are boring, but the nice thing about this is that we have sort of the two ends of the spectrum now, right? The 2 gradings are H1 is as big as possible. It's the M is the smallest. And then we have the other side, which is M is as big as it can possibly get. Yeah, but we're hoping to do more with this, but this is what we've got now, and I'll stop there. Oh, is it? Oh, did I have more time?
Perfect.
Okay.